All right, so it's 2:02 now. Let's get started. So hello everyone, welcome to Ask Seminar Series. This is John, the seminar coordinator, and I will be with Katja Medney, our communication manager, to moderate this seminar. And also joining us include our director, Nas Peter, and our associate director, Ralph Ferrero, and assistant director, Eddie Negri. And Ralph will be introducing the speaker. Just so you know that the seminar, the recording will be put later on our YouTube channel. And after the presentation, we encourage you to ask any questions you may have. And you can do so by sending us a chat message or just use your mic to ask a verbal question. And so before the speaker gets started, I'm going to hand this over to our Associate Director, Ralph Ferrero. And Ralph, please go ahead.
Yeah, thanks, John. And yeah, I'd like to welcome our speaker, Dr. Katja Friedrich from University of Boulder, Department of Atmospheric and Oceanic Sciences, where she's a professor. The type of work she does, I think we're gonna hear about shortly, but it should be a very interesting topic. And let's see, she got her degrees in Germany. Most recently, her PhD is from the University of Munich. So with that, I'd like to turn it over to her and look forward to her talk.
Thank you so much. So the title of the talk is Making Snow and Advances in Orographic Wintertime Cloud Seeding Research. And I changed the title a little bit just to make sure that I'm just talking about orographic wintertime cloud seeding. There are a lot of different types of cloud seeding, and the research is very different, and the results are a little bit different, and we can talk about this later on, but I'm just focusing on that. But before I want to start, I also really want to introduce my team. So this is really a great team effort that we were pushing this orographic cloud seeding research forward. So I have my colleagues, Jeff French, Bart Geertz from the University of Wyoming. We have Sarah Tessendorf, Lulin Shu, Cici Chen, Jamie Wolf, and Roy Rasmussen from NCAR. And we have Bob Rauber from the University of Illinois. And then we have really a large amount of students that got their degree through this cloud seeding research. And I just highlighted here a few, but there are really a lot of people in the background. So, and I really want to say that this is a very very fruitful collaboration between our four institutions that got really the orographic cloud seeding research here of the general conspiracy platform really to a different scientific level. But before I want to, so why is this? What is the motivation behind this? I'm originally from Germany, and so when I came here, I was also, why are we cloud seeding? But once you start living in the West, you will really see that there's a water problem. So you see on the left-hand side, there's the water stress level, and then there's the allocation of the Colorado River. And you hear this all the time in the news that there's basically not enough water. And the reason for that is twofold. One is that even predicting precipitation, and there's a big variability, natural variability, and now there's also large variability due to climate change. There's another really interesting part to it, is that really the population in the West has dramatically increased, as you can see here in this slide. And so, and as people move out west, primarily because of the weather and because it's nice and warm and dry, the demand for water gets really high. Plus, there's the demand from agriculture, there's the demand from hydropower, and then another interesting fact is that most of the water in the West is basically stored through the snowpack. So snowpack is pretty efficient because you don't need to have a dam. And it used to be that you have the snowpack, it accumulates over the winter, and then it slowly melts starting April 1st, and then the snow melt trickles down to the different basins into the rivers, and then basically agriculture could take the water out in early spring, summer for irrigation. And that used to work pretty well. Now that the snowmelt occurs a little bit earlier, so the water flows down earlier as well. So there's a mismatch starting now, but still snowpack is a pretty good way of storing water that can be used in the summer. So that's why this orographic cloud seeding started to develop in the West and the primary focus is increasing the snowpack in the winter so that we have enough water for spring and the summer getting us through the year. The interesting fact is that a lot of the water that is generated through cloud seeding, the goal is not so much to really increase the water for agriculture, but also have enough water for hydropower. So have enough water in the reservoirs to generate hydropower. So these are the goals for cloud seeding. But before I started, I just present this. Bob Bravo presented that at an AMS meeting, which is really interesting because it explains a little bit the entire conspiracy about cloud seeding and all the misconceptions and opinions that people have. Okay, so these are his slides. And so as we have shown this timeline, and in order to make it a little bit more entertaining, Bob actually put in some highlights, different years and different artists, to see where we came from Frank Sinatra, I think, to Adili. Okay, so how did we start it? So basically in 1946, Vincent Schaefer of MIT, he created ice in supercooled liquid using CO2. And then in the same year, Bernard Vonnegut basically recognized that we can use silver iodide, which has a crystalline structure very similar to ice. We can use that to basically seed these supercooled liquid clouds. And so once they started doing this, we basically went into this, what Bob calls the Wild West of weather modification, or the Wild West of cloud seeding, because now people were basically going out and promising everyone that we have this amazing technique where we can suddenly generate precipitation. And here's just one, a few quotes that come out of this Skywater, Project Skywater, with this weather modification program from the Bureau of Reclamation. And so basically they say it for free for all period, a flock of quick buck artists who traveled around the countryside, convincing weather-hungry farmers that they had the secret to hold the Indian rain dance. And then they further said, like in 1951, one seeding company had almost 300 million acres of the United States under contract, and they were trying to do weather modification. And so the interesting part when you do about cloud seeding research is there's really, the industry is pushing the research. So the industry goes forward, does these things, and I'll show you more examples. And there's, I wouldn't say no, but there's sometimes very little scientific proof whether it works or not, but they're basically just going out and trying to do it or doing it to make money or to generate precipitation. And that was similar in the 50s and 60s. So as we're moving on, we are basically, as people were doing this without really a lot of observations to do that, the federal government basically came in and said, okay, we need to do something as well. So they formed an advisory board in 1953, and then the committee in 1957 recommended that basically National Science Foundation, NOAA, should basically have sponsored research programs and provide contracts to do some weather modification. And you see, this is the 50s. These are not executive order things. It took like 6 years to form a bill that basically gave the National Science Foundation the authority to build this research. And so really, the weather modification research started in the 60s with different projects. And I would recommend, Bob Bravo wrote a nice overview article about cloud seeding, also globally. And so there were a lot of programs that were sponsored by the National Science Foundation, by the Bureau of Reclamation, and by NOAA to basically do sponsored research. So again, at that point, again, the numerical modeling was really in its early stage in terms of what we can resolve. And even the observations were really cruel. So a lot of the results from this kind of research were not really straightforward. So they were very arbitrary. There was also a little lot of fighting between the scientists. We had this group of people who said, yes, we can see a signal, cloud seeding works. Then they had the other group of researchers that, oh, we don't see, it doesn't work. And so there was a lot of fighting going on. There was a lot of arbitrary results. There were a lot of good results that came out as well, in the sense of, okay, what are the clouds or seedable clouds? What are the conditions under which cloud seeding works the best? And I'll talk about this in a second. So basically, starting in 1991, federal agencies actually stopped cloud seeding or funding for weather modification. And again, this was two faults. One was that we didn't really get a lot of good research out of these last 20 years. And then the other reason was that now we basically moved more onto the anthropogenic weather and climate modification, basically climate change, and that's where most of the funding came in. Okay, and then in 2012, we started to propose the first experiment called ASCII around cloud seeding, because we now had numerical models that we could run in LES mode, like 300, 100 meter. We had modules that basically could simulate what happens in a cloud as we are putting silver iodide in. And so we basically had better technology and better numerical models that we're trying to convince NSF to say, okay, we need actually have another experiment. And just to know that since the 60s to now, cloud seeding was going on no matter what. I'm just presenting here the research behind it, but agencies cloud seeded through the entire time. They also did their internal research, because again, most of the cloud seeding is done by private industry. And so they are also they need to justify why they're doing this. So they did their internal research, but it was interesting that that cloud seeding is going on no matter what. And then we had a second experiment, SNOWIE, and I will tell you a little bit about the highlights of SNOWIE that we proposed, or we actually conducted to continue the cloud seeding research. Okay, so interesting enough now, 2025, all of the Western states are currently doing orographic wintertime cloud seeding. There are a few states that are starting the program, or they have a test program, like Montana, Washington, and Oregon. Yeah, it's interesting. And you see some of those states are actually investing a lot. Again, we are a little bit behind in terms of research, and I'll highlight this in a moment. So you see the demand, the need of water in the West. And again, usually what I say, cloud seeding is just part of the entire water demand, but you see that all those states are actually doing it. Okay, so how does cloud seeding work? Okay, so the cloud seeding is basically works on this principle that you have these supercooled orographic clouds, and they are relatively shallow and they're relatively warm, with a relatively warm cloud base. And once you have a really warm, relatively warm cloud base, you don't have a lot of ice nucleating particles. So here's just a schematic from Paul Demott, where he combines different measurements and different ice nuclei concentration. And you can see as we are reaching colder temperatures, we have so much more ice available compared to these warmer temperatures. So we have these supercooled liquid clouds hovering in the air. And again, that's why we're doing orographic wintertime cloud seeding, because these orographic clouds are rich in supercooled liquid, and there's also not a lot of turbulence. Okay, so the idea behind cloud seeding is you have the supercooled liquid clouds, you're flying an aircraft above those, and you're basically injecting silver iodide. Silver iodide works very well as a seeding agent between -3 to -6 degrees Celsius. And once you seed the cloud with silver iodide, you basically, ice crystals start to freeze, and they start to continue to grow through the Berger and Findereisen process, or through riming and aggregation. And now you're basically extracting the liquid out of this cloud through microphysical processes. And again, if you do it in an orographic environment, you basically, through orographic lift, you're continuously providing the atmosphere with supercooled liquid that then basically can be taken up by the silver iodide. So this is the underlying idea of cloud seeding and how we are proceeding with that. So again, cloud seeding can be done in two ways. We can have airborne cloud seeding. So you have these seeding flares that you can burn at the end of the wings. We call that in cloud burning, or you can have these flares that you can ignite in the aircraft and then you drop into the cloud. So again, it depends on the conditions. If you have a lot of supercooled liquid and the aircraft cannot fly through the cloud because of freezing, they would basically go on top and seat and drop those. And then sometimes if they can fly through the cloud, they would basically do this in cloud burning the silver iodide here on the wings. The other way you can do airborne seeding is from the ground. So this is just a photo of a ground-based generators, and you and I'm just putting in here the chemical composition, how you can generate AGI. So you're basically burning the silver nitrate here in these containers, and then you're releasing the particles, and you hope that these particles are getting lifted up into the air to the cloud base, into the area where you have supercooled liquid. So again, there are two different methods. One is relatively costly because you need to have an airplane and you can just see it over a certain time. But you can be pretty precise because you can fly into the area of supercooled liquid. A lot of times these aircrafts also have measurements, so they can measure the amount of liquid water content. Or you have a relatively cheap method, but you're really relying on the boundary layer conditions. You really rely on the vertical velocity lifting up these particles. Okay, so here's just a video that I wanted to show you how from the aircraft, if you're burning these silver iodide flares on the side of the wing, and you're basically distributing the silver iodide in the cloud. Okay, let's move on. Okay, so we've been working, NCAR has been working with Idaho Power Company. That's a power company in Idaho. And they were basically working on using numerical models to develop a forecasting system that Idaho Power can use to predict at what time they should cloud seed and what are the conditions optimal for cloud seeding. So again, if we have a storm coming in, what is the time period where you have the highest amount of supercooled liquid? And so they've been working together for over a decade before we actually started the SNOWIE project. But based on this collaboration, we then came up with the idea that we really wanted to have an experiment that piggybacks on an operational seeding program, and we can just go in and validate what they are doing. And when we designed the SNOWIE experiment, which is called Seeded and Natural Orographic Wintertime Clouds, the Idaho Experiment, really the main goal was to collect data so we can actually run our numerical models. And you will see that this actually turned out in a funny way. So the overarching goal for this experiment was to first understand the natural dynamics and microphysical processes. And again, these are natural clouds. What does these natural clouds look like? How much supercooled liquid do they have? Under what conditions does it work? How much ice particles do they have? And so on. And then once we develop that, is okay, what is the role of silver iodide? So determine the physical processes by which cloud seeding with silver iodide impacts the amount and the distribution of snowfall. So this was the overarching goal of SNOWIE. It was located in the Payette Mountains. So this is the Snake River Basin. These are the Payette Mountain. Boise is located here. And this is just a map. And if you ever have the chance to visit Boise, this is so beautiful down there. So I'm always the ambassador of Idaho. Okay, so here's the experimental design. So this was the seeding aircraft that we had. You see they have a lot of also CDP and cloud imaging probes on the wings of the aircraft. And then they had the seeding probes. And the idea is, just look at the green lines for a moment. So the idea is they are basically flying the aircraft upwind of the Payette Basin, always perpendicular to the wind. So if you have a westerly flow, they would basically go back and forth, usually place like six to eight seeding legs back and forth. And so the idea that we had is we are now using our ground-based observations from ground-based radars, from snow gauges. We had radiometers, and we had the University of Wyoming King Air, and the King Air would basically fly parallel to the wind, perpendicular to the seeding aircraft. And so to observe the seeding material or the seeding impacts, again, once we seed here, the seeding material should basically fall in this area. The other two were basically just different wind directions. So we have westerly winds, we have southwesterly winds, and we have west-southwesterly winds. And so that was just the setup. As I said, we had the Wyoming King Air as the research aircraft flying back and forth. We had in situ measurements, droplet imaging, or particle imaging, droplet probes. We also had a LiDAR and a W-band radar that provided observations. In addition, we also had ground-based radars, the Doppler and wheel radars deployed at Snowbank and Paco John, and we had other instrumentation. We had soundings, distributed radiometers to measure liquid water content. And then we also had snow gauges and disdrometers to measure the snow population or the distribution. Okay, so from numerical models, we already knew that if we are seeding or doing this aircraft seeding and we're flying back and forth, and if then our hypothesis works, that we have supercooled liquid clouds, we are basically freezing, we are glaciating those clouds and generating snow. What we should see these zigzag. Again, the zigzag comes from this aircraft starts here, deploying the seeding material. And so this is the first part that's being advected with the wind, and versus then the latter part, which is then advected a little bit later. Again, the coloring shows you how much microphysics is going on, how much snow we can produce. So we should see these zigzag lines, and we saw these zigzag lines in numerical modeling. So if you're flying the aircraft, we should basically see a change in microphysics as we are flying through the cloud. So the seeding aircraft would usually fly on top of the cloud, and then the research aircraft would basically fly usually 500 meters to kilometers below the research aircraft, again, for safety issues, but also because we wanted to fly through those seeded clouds. And this is just a cross-section. Again, if you're putting these burn-in-place flares, or we're dropping those, again, we are glaciating the cloud, the ice crystals grow through rhyming and aggregation, and then eventually fall through. So this is the underlying concept of this experimental design. Okay, so we conducted this experiment in January and March 2017, and this was a very, very active year. So we had 24 IOPs, and I've been doing a lot of observational work, but 24 IOPs is a lot. So we have 19 cases where we did cloud seeding, airborne cloud seeding. We have, we have 19 cases where we did airborne cloud seeding. We have 3 cases where we did ground-based seeding. And then actually at the end of February, Idaho Power had to stop their seeding activities because they have a threshold. Once the snowpack gets to a certain depth, they're stopping cloud seeding because of flooding issues that they're expecting then in the spring. So we were continuing with our experiment. And so we also have 3 cases where we had no seeding and we could study the natural clouds. So here is just then 4 aircraft transects of different cloud types. So we would basically could categorize our events or even our individual flight tracks into where we had a single orographic cloud. Again, this is the concept. We have a relatively shallow cloud where we expect a lot of supercooled liquid water, and we're basically seeding the cloud top with INP or silver iodide in order to enhance the glaciation. We also have split clouds. Again, you have this orographic cloud underlying, and then you have a upper level probably ice cloud, but they're not connected. Sometimes we had these deep clouds where we expect a lot of active microphysics, and then and most of the times we had a mix of everything. And again, this was change. You can see this today we have changes in space, and we have also changes in time. And this is basically observations that we were taking along the wind perpendicular to the flight track. As you can see here from west to east, it's here the same flight track. Okay. That's the first highlight. So again, as I said, this was a really active year. We deployed 1 radar at a place called Snowbank, which I mean, should tell you what you to expect. So we had the radar there. We had little huts there, so the radar operators could stay there overnight, and you could see we had the snowmobile in. And then as we are going on in the season, the hut basically disappeared. We had to dig a tunnel and then some breathing holes because we had so much snow. And at the end, actually, the entire radar was covered, and we couldn't really use this particular radar for I think for the last 4 IOPs. This is another image, and this was a location that actually had an FAA radar. So we thought, okay, this is actually pretty cool because they're cleaning the road. And they were actually cleaning the road, as you can see here, but we still had a lot of snow. So this is another location that was a little bit windier, so we had a lot of snow drifts, but at least the radar was out of the deep snow. Okay, so let's move on and let's discuss a little bit of the research. So the first thing that was very new and innovative during this project was that we could actually see these seeding lines as we hypothesized in these zigzag lines. And so this is one case. This was really the first case where we saw that. And earlier I said we had some senior scientists, Bob Rauber and Roy Rasmussen, who've been doing this for 50 years. And I mean, they were almost in tears when we saw that. So this was one image that actually our students sent us and said, look, this is weird. Look, we see these weird lines. And here you can actually nicely see this kind of zigzag line. I'm running this again. Again, this is the seeding aircraft. This is the research aircraft. And we see radar reflectivity from this radar. And so as we are starting this, on the left, you see what we observe, and on the right is basically what we extract, what the seeding signal is. And here you can see these are these zigzag lines. You can even individually see where we are dropping these individual flares versus when the seeding aircraft did in-cloud seeding, where it's more like a straight line. So that was really exciting that we saw that. And we could also see that in the aircraft radar. So this is this is an X-band scanning dual polarization radar, but I just showed the radar reflectivity. But we could also see that in the aircraft radar, again, the aircraft was flying here back and forth, so basically intercepting these seeding lines, and we were able to, once we know where we're dropping the flares and how the flares are advected with the winds, we can continue tracking those seeding lines. And here's like one line that then evolves with time and eventually precipitates out. We have another line that evolves, and it's really interesting to see also how these lines evolve, like this, for instance, that basically generates precipitation, it falls out, versus this line where you see you have the seeding lingers around a lot. And what really was new to us, or we were really surprised about, that we see a lot of reflectivity at the upper level, which indicates either you have supercooled liquid that is generated and you still have enough silver iodide taking up the supercooled liquid, or you have some kind of latent heat that's basically pushing your smaller particles higher up in the cloud, or a combination of both. Okay, so then we were so excited, and actually we went back. This was the previous day, and we looked at the radar data again. Most of the time we saw these seeding lines when there was very little background precipitation. So here, this is your background precipitation here where we're cutting it out. This was also an interesting case because the seeding aircraft changed their track. So now you will see those seeding lines parallel, not as a zigzag, but that was just basically because the seeding aircraft changed what they were doing. You see there's the seeding lines. You see also there's a lot of natural precipitation underneath this as it evolves. Okay, again, we could see that in the different lines, but then we also wanted to look at the in situ measurements, not just at the reflectivity and tracking it. So here on the right are some of the measurements that we took as the King Air was flying either underneath or then through those seeding lines as they evolve. And on the right-hand side, you see a particle image. So these little dots, this is not dirt on your screen. These are supercooled liquid droplets. And then you can see which were observed here underneath the seeding signal. And then with time, you can see that ice crystals are forming and they're growing in size. And we can see the same signal when we look at the CDP, the Cloud Droplet Probe, which basically measures really small particles, which we can identify as supercooled liquid. During the first leg, we see a large number of small droplets and a small number of larger, a high number of small droplets and a large number of large droplets. And then with time, you can see that there's a shift, that the smaller droplets actually growing in size. all these particles grow in size. So there was another indication from the in situ measurements that really this process of turning supercooled liquid into ice. And here's another observations. Again, you see the images on the top, and then you can see the supercooled liquid water, which is the blue line. So early on, we have these kings or these enhanced supercooled liquid water contents. And then with time, you can see that the water actually turns into ice. So very little ice at the beginning, and then we're turning this into the more ice as time progresses, and microphysics does this job turning supercooled liquid into ice. So and again, these were very new results because people until then have maybe seen like a little bit of this, a little bit of that, and a lot of interpretation. But with this data set, we were really able to track from the time where we're putting the silver iodide into the cloud to the time where we're basically generating precipitation at the surface. So that was a very new revolutionary idea. And since we had radar data, we actually were able, we can now actually quantify how much precipitation can be generated through observation. So we took the radar data, we converted radar into equivalent snowfall, and we generated these maps and basically accumulated everything. And then I was converting the acre feet into cubic meters. But again, for people who are not really familiar with those units, I was also converting it to Olympic-sized swimming pool. So again, you see we can generate 50 to 136 amount of water equivalent to the size of Olympic-sized swimming pools. And so, and this was also really new because first of all, quantity is a really difficult task, but it also showed us that these are not really large numbers. So, and again, that shows us why it is so difficult to quantify, because the numbers are really, really low. And the reason why we were able to do that during these three cases was basically because we didn't have a lot of background precipitation to begin with, and we could isolate this. So again, think about this in the context of a big cold front coming through with a lot of deep precipitation, and then you're seeding a little bit, you might not even see the seeding signal. Okay, so what we also did was we were trying to quantify this through snow gauges. So that's a method that people have used in the past, and again, not really successful. But since we knew when these seeding lines passed over the different gauges, we could then identify the time and see whether if there is a change that we can see in the precipitation amount. And that was really tricky because first of all, you can see even when you have something relatively clear where you have no precip before, the seeding line passes over, and then you have no precipitation afterwards, you can see this increase and can attribute this to cloud seeding. But again, the numbers are really small. 0.2 millimeters is really not much that you generate, and also not much, a really small number to measure. And again, you have difficulties once you have background precipitation. This is another case. You see, you have a little bit of snowfall before it stops here, so then you have a little bit in increase. Sometimes we have gauges where obviously the seeding line did not actually reach the surface as it passes through. So again, this some people have actually seen, or also these 0.25, 0.2, 0.3 millimeters increase through seeding, but this is a small number to measure. Again, that confirms why this has been so difficult in the past. Okay, so I want to move on and show you some other results that we did. As I said before, we were also looking at natural clouds. So that is a study that Troy Zaremba did. And so the first thing he was looking at, again, we're looking at orographic clouds. We want to know where's the supercooled liquid. And the supercooled liquid can be advected, but it's primarily in an orographic setting. It's primarily generated through orographic lift. So again, we wanted to know where are the updrafts and the downdrafts. So what Troy did was he took all the 200 flight legs that we were flying, and again, we were always flying parallel to the wind, and he was basically just averaging all those flight legs, and this is what he got. So you can see this is the terrain underneath from west to east, and you can really clearly see you have an updraft as you go up, you have a downdraft as you go down the ridge. You have an updraft as you go up the ridge, downdraft, updraft, downdraft. Again, the higher the ridge, the larger the updraft. Again, theoretically, we know that, but we were really surprised to see it at this level. And we even used 300-meter wharf simulations, and we got the same results with these really stationary, fixed orographic updraft. And that was really interesting because, again, this is where you have your enhanced supercooled liquid that you can deplete through seeding. He also did another really interesting study. He looked at transient features. So he looked at gravity wave, convection. He looked at surface turbulence. He looked at cloud top generating cells. I don't know. He has an entire list of these things. Again, same method. He's basically looking at, or these are individual case studies, but he looks at the vertical velocity from the King Air radar. This is the radar reflectivity, and looks at, okay, where do we have the updraft? Where do we have the downdraft? Again, in the updraft, these are our areas where we have a supercooled liquid. Here is a deeper convection case where you have updraft mechanism. And then what he did in the next study, he basically linked those updrafts to supercooled liquid water amount, number concentration, and you can see that, again, you have stronger updraft, you have higher supercooled liquid water, you have a higher number concentration. And again, this is all something that we are expecting, but seeing it so clearly in the observations was really something that we didn't expect, that it really comes out so clearly. Again, higher lift, higher terrain, higher number concentration, higher supercooled liquid water, higher number concentration. And we can also see like a little bit of a those number concentrations were shifted downwind. Okay, so then another study that actually Sarah Tessendorf of NCAR is leading is the role of these cloud top generating cells. Everyone is talking about cloud top generating cells, but in an observational standpoint, it's always an afterthought. We see these things and say, oh, we're getting so excited. But the way we are setting up these experiments is often not that we are really focusing on those. So here we have an okay data set to study those. As you can see, we had some flights that we were going through these cloud top generating cells. Again, the idea is that they are generated through cooling. We are creating these up and downdraft pattern, relatively small, so sub-kilometer space. And as we have those cloud top generating cells, we think that the updraft, basically we are generating rhyming, and then in these downdraft, these are basically shredded like secondary ice production ice crystals that can then serve as INP. And there are a lot of studies from Bob and House that these basically INPs are important for generating precipitation. And they think in a study that they did in the 80s that these cloud top generating cells can probably attribute to 20–30% of precipitation increase. Again, it's really difficult nowadays with this observation just to repeat and really quantify those observations, but we have some good cases where we can actually do that. And here's some in-cloud measurements of those almost rime particles as we're going through these cloud top generating cells. That's the radar reflectivity at W band, and that's the vertical velocity measured by the radar. Sarah went further and used the in situ measurements to compare like what is the microphysics in those cloud top generating cells versus outside. So the green is outside, the purple is inside, and you can see for the different cases, usually you compare these during the same case, the liquid water content is higher in those, not always, you see there are some cases where it's not the case, but it's usually higher in these cloud top generating cells. Again, these are areas, local areas where we can generate supercooled liquid. So again, for us, we're always looking, where's the supercooled liquid, where's the ice? Okay, but you can also see that actually ice is also higher in those supercooled liquid, going back to this principle that you have ice crystals that rime, but also you have ice crystals that shed off and can use as INP. And then we also have higher reflectivity in those cloud top generating cells. And again, we haven't really made the study yet, but we think that this has an impact on the surface precipitation. Okay. Another study is now that we have those 24 cases. One of my students, Ted Wittock, he started this analysis and looked at how do those different cases compare based on the cloud structure? So we are looking at liquid water versus ice water content. Again, the underlying idea is that in the seeded clouds, we have a lot of supercooled liquid water and we have very little ice. And this is basically showing us here, these red numbers show us the cases or the times where we did observe these seeding lines. And again, the cloud top temperature is relatively low. And then in other cases where we have enough ice, these are these deep clouds that are pretty efficient. And this goes back to a topic that I will raise later. We also need to talk about seeding efficiency. So now that all these states are doing cloud seeding, and is really how much silver iodide do we really need to put in? And my theory is that at the moment we are putting far too much silver iodide into these clouds to do the cloud seeding. And then the same thing, when we do cloud seeding, we have the drizzle research that we have larger particles with lower number concentration, where we see the seeding effects. Okay. And then the last part that I just want to highlight is the modeling. And this is really something that Lu Lin and CC at NCAR spearheaded. This is a simulation that my student Xixing did, and these 300 meter simulations with their WRF weather modification module, which is based on the Thomson-Idaho microphysical scheme. And so we are using those models to understand microphysical processes, because again, we wanted to start out remember, SNOWIE started out to actually being based on collect data for model validation. So we wanted to really understand what are the microphysical processes and are the models capable of doing that. And here is an example of one of the cases where you can again see the zigzag signal, and here the color coding here is the ice water content. And the nice thing about the modeling is you can run your model with seeding and without seeding. And the initial idea was actually that we are making the model good enough so we can actually run these simulations, so we can quantify the efficacy, that we can quantify the amount of precipitation we can collect. Because the problem with observations is we never know what is the reference. Once we see the cloud is seeded and we don't have a reference. The models allow us this combination. And again, this goes back of how much precipitation can we generate. We don't want to know it from case to case. We want to know it over an entire winter. And that's the idea of this modeling. So we did a lot of case study modeling. Again, here's a cross section through those and shows you the evolution of ice. I think this is the ice water content here. Color coded, and you see depending on the amount of AGI that we are putting in here, AGI is depleted and we are generating more and more ice as time progresses, and that ice basically falls down onto the ground. Again, with the model, we can do these studies on like how much AGI do we really need to put in. So this is a really nice tool set or toy that Lu Lin generated. Okay, I think I have a chat question. Okay, oh no, sorry. So this just came up here. Okay, and then the last thing that we are doing is these ensemble modeling, again, that Lu Lin and CC are spearheading. So we're using WRF weather modification to run this as an ensemble. We have 32 members. We have the 24 cases that that I mentioned earlier from SNOWIE. We are running it as a modeling framework, as a seeding framework, and without seeding. And again, the idea is looking over the entire 24 cases and see how much precipitation can we generate. And so here's just, we are in the middle of them. I should have showed you the Excel sheet of like who is running what model simulations, because that was actually really funny. I don't know how they could keep track of everything. And this is just like really the first results that CC presented at the AMS, where we're looking at the different IOPs, the different seeding cases that we had. We're looking at the different in precipitation. Again, we have a long discussion of even how to analyze the 32 members, and whether we just take the mean or whether we are extracting the ones that totally are out. So and then when we have that, we can basically look at these seeding impacts, and we can actually go back to our observations and see whether we see the similar thing in the observations. Okay, so So these were the highlights, and just as in conclusion, so again, SNOWIE is an amazing data set. Everything is out in the public, so if anyone gets interested in that, really these were breakthrough observations, and a lot of the cloud seeding activities that are currently ongoing are based on the studies that we did, and this was really the first studies that we put out where we scientifically quantified and really looking at the processes as well as quantifying those processes. Again, the instrumentation, again, the King Air was amazing. The ground-based radars, we can run it at such a high resolution that we can see a lot of the structures. And again, the model capability is just really astonishing. Yeah, and so again, it was a lot of like application and outreach. Again, we could understand more, okay, what are the conditions under which we see it? What are really the impact? Well, how do the natural clouds look like? I think this is really important if you're running a seeding program. And again, outreach, I'll talk in a little bit, because again, there's just so much conspiracy around cloud seeding. And again, I have people, they complain about too much precipitation, too little precipitation. And so here we were able to quantify that in observations and show the public, like, how does it really work? How much can we regenerate and things like that? Again, ongoing challenge that we still have is efficacy, cost effectiveness. Again, a lot of these states are doing this. How does cloud seeding? I think the wintertime cloud seeding is really far ahead in the research. Again, what about summer cloud seeding? What about hail prevention? I mean, these are areas which I think are not really well studied. And again, you cannot believe how much time I spent with educating people about cloud seeding and the misinformation. Okay, so what is next? So what do we want to do next? So the next thing that we really want to tackle is the ground-based seeding. I mean, airborne seeding we thought was actually pretty easy because we could track it. Now the question is about ground-based seeding. Again, we need to understand the boundary layer conditions. We need to understand the stability, lift. Again, we are in an orographic environment where you have a lot of stable air in the valleys. We need to still understand like how much supercooled liquid ice do we have, and we can't track it because silver iodide gets dispersed so widely when you do ground-based seeding. I just want to show you an image that shows you the simulations where we are using WRF output and we are simulating radar. This is with seeding, this is without seeding, and this is the differences in the reflectivity in between, and this is like the accumulation. If you cannot look at 4 simulations at the same time or animations at the same time, just look at this image here and you can see that's basically what we can generate in a model from ground-based seeding. Again, you have these highlights. You can, when you go slowly through those images, you can see some seeding generators don't produce anything. Others that are higher up produce a lot of precipitation. Again, we need to verify this with observations. Again, seeding efficacy, efficiency is still a big problem. Big question, like how much snow can we produce? It depends on the season. It depends on the area. Again, industry, they are starting to seed with drones. I don't know really how they do this, but again, where are they supposed to fly? How? We have no idea. There's a lot of shadow route ground seeding with different agents. We haven't really tested any of this. I think that's it. Okay. Thank you so much for your attention, and I'm ready to take questions.
Thank you for that. So if I mean, everybody can just raise their hand and ask their question verbally or ask the question in the chat. We already have a couple of questions in the chat, so we can go ahead and start with that. Ruya, did you want to ask the question verbally?
Oh, yes. I'd like to know how this Thomson microphysical scheme did compared to the observation. You know, if there's any obvious issue with the scheme or anything like that. Thank you.
That is a good question. So I don't know. I mean, again, the experiment was 2017. We are more than 10 years later. We did so much. We spent so much time on validating those models. So the things that we realized are really important are the driving data set. So ERA 5 was the best estimate. Again, we did a lot of sensitivity studies, how big we need to do our domain. We also realized that what is really important as a first step is to get the cloud structure right, whether it's a deep cloud, whether it's a split cloud, whether it's a single cloud. So we spend a lot of time, the driving data set. Another really important one, and again, this varies from IOP to IOP, is the wind direction, the wind speed. If we do get that wrong, again, everything is dispersed really, really differently. So in the end, what we compared then liquid water content and ice water content. And again, we didn't really did any other simulations with other microphysical schemes, but I can just tell you that the variations are really wide. That there are some simulations, again, it depends sometimes on little things, like, again, as I said, the wind direction or the turbulence, stability, that then things are dispersed relatively differently. And again, we're comparing everything to the cloud level. So if the model is not capable of even getting the cloud structure right for whatever reason, the comparison between liquid and ice water content is totally off. So I can't really give you a good answer to that because we didn't test other microphysical schemes, because the weather modification scheme only runs with the Thomson scheme. But we found that there's really the liquid and ice water content depend on so many things. We did sensitivity studies on the CNN concentration. So again, we put in 30%, and suddenly it actually represents the clouds much better. So I'm not a modeler. You figure it out, but it's complicated.
Thank you. Thank you.
Lars Peter also has a question. You can go ahead, Lars Peter.
I think Amin was first, actually. But I can go ahead and ask. Thank you very much. Very interesting stuff. Of course, it is, as you said, it is tremendously controversial. And I think this is one reason why many scientists have shied away from it. And the other is, of course, the difficulty in it. In a chaotic natural system, it's difficult to tease out the signal. I had a very naive question. It's the first sort of comprehensive presentations that I've heard about the impact of cloud seeding. No, it's the second. And the first one I heard from a completely different area, different environment. It was cloud seeding in the Middle East, and the purpose is completely different. The approach is also completely different. They actually seed below the cloud, never from the top, as I'm sure you know. What's the difference? Is it because, I mean, they weren't really doing this in strongly convective environments. It was basically what I would call stratoQ that they were trying to tease moisture out of, and there just wasn't very much there to begin with. So what is the difference? Is it just is it the different environments that you're trying to initiate, or is it a different outcome that you are trying to create, or what?
I think it's the same outcome, because you want to get the seeding
Yeah,
material where the liquid is. So I think it's just different. So if they're doing, if they're flying, and again, this is the idea of drones, you're flying the drones below the cloud base and then hope that the updraft basically lifts everything into the cloud.
That is what they did. They were flying just below the LCL.
Yeah. So I think with the because when they're flying above the cloud, they're basically dropping those silver iodide into the cloud, and then it burns for about 10 minutes as it flies through.
Okay.
So, and then dispersing the silver iodide into the cloud. So it's just a different method. Again, I think when people want to start seeding with drones, they would probably do the same thing, going below cloud top. Again, the problem here is very mountainous terrain. They can't really fly that low. I mean, even with the King Air, we were trying to fly as low as possible, but the mountains are just in the way.
That makes sense. I mean, this was in the UAE, which close to the coast is relatively flat. It is mountains in the hinterland, but it's flat near the coast. Okay, thank you.
Yeah, you're very welcome. Shall we go to the chat? I'll quickly answer the question. Seems like positioning ground seed stations near the top of the ridge on the windward side would be a good thing to do. So yeah, most of the cloud seeding, the ground-based seeding generators are on mountaintops to avoid the surface blocking. But again, the question is, how deep is the stable layer? So these are all questions that we are trying to understand. But again, so these are all ground-based generators, and you can see in this simulation where you can see the ones that are higher up, like, can I stop this? Yeah. They are basically generating something, these two here, while then others that are a little bit lower, they do not really generate any precipitation.
Yeah, thanks. I just wanted to follow up. Yeah, I mean, that's interesting. I was just wondering though, I mean, in terms of making it work, it seems like having a good handle on the Froude number would be a good thing to do as well when trying to use the ground stations. If it's not, if the Froude number is not ideal, if it's like subcritical, it might not be advantageous to employ at that point a ground station because the stable layers are sufficiently stable compared to what the wind can overcome.
And that is something that we want to address with this follow-up experiment. But you can also see how this is the underlying terrain. So you have these different valleys, and it's really difficult how to be evaluated. The other thing is it's very, very, I mean, we have a road here, and everything here is really remote. So you can go in with snowmobiles, and it's really difficult to make these measurements, but you're absolutely right. But again, how stable is the boundary layer and how much fluctuation do we have? It also probably depends from day to day. And I'm sorry I interrupted you. You probably had a second part to your question.
No, it's fine. I'll let others chime in, but thank you.
I mean, do you want to go next?
Yeah, sure. So you very briefly mentioned the conspiracies and also misinformation, all that. And Lars also mentioned the Middle East, which is the perfect region for that topic. You hear all these terms like cloud thefts, cloud stealing, and all that. So I was wondering what would be a potential outline for study that you would give to address that question, like conspiracy theories. If you believe that the cloud seeding cannot really, that I do believe, cannot affect downstream countries in a significant way. There are different numbers, like it can be like the efficiency could be between like 5 to 25% or so. If you really believe the 25% and the activity is so significant that they see all the clouds, then in a normal year you would expect that the downstream country could be pushed into a dry condition. But so what would be the study that you would recommend to do for that region specifically to address this question? Thank you.
Yeah, that is a good one. So our entire group, we are trying to move away from the percentages, because the percentage of what? Because it varies from year to year. They're saying, okay, 25 of annual, but you see in the cases that I showed you, there was no ground-based precipitation. So basically we did 100%. So it is really misleading, this percentage-wise. So that's why we are trying to quantify that in amount of water rather than in a percentage, because, we also realize that it really depends from storm to storm. It depends from area to area, and it depends from year to year. So that's why these numbers are really misleading, and people saying, oh, 5 to whatever, 35%, but honestly it's from 0 to 100 and you pick a number, because sometimes it can be efficient. Again, it goes back to how many, we are trying also to understand what's the percentage of efficient cloud where we have enough ice nucleating particles versus inefficient cloud. So that's why the quantification is really at the early stage, even though a lot of agencies putting out those numbers. But again, I can debate any of those numbers, and they can double or go up and down as you want to. So that's the number one. A study for this. So then it goes back to this conspiracy. I hear a lot of people saying, oh, we are concerned about the flooding because cloud seeding basically treats so much and we have the flooding. Or the other group that says, oh, you're creating these drought conditions. So we showed in our studies that you can actually generate a lot of precipitation from cloud seeding. You can generate precipitation, but it's just a tiny bit. And we talked about Idaho Power about this, and they said, yeah, sometimes it's just enough to get our reservoirs over a certain level so we can keep the water level and we can still run the hydropower. So they were not really concerned that the numbers are really small. But what we see so far, the numbers are really small. You saw in the ground-based the rain gauges, it's 0.25. I mean, this is not a lot that we generate. So we think you're actually not generating a lot from cloud seeding. which also is supported by why there was so much discussion about this last 50 years, because there's really no clear signal into that. Again, going back to the trout conditions downstream, and I had this a lot. I mean, you cannot imagine how many senators contacted me about this. If we are seeding in Idaho, what happens to Wyoming? Okay, so again, we can use those models to really quantify what is the difference in precipitation. What I always say, and we haven't done that, that's something that we should do. What I usually say is, again, we are not generating a lot of precipitation out of these clouds, so we are really not taking a lot out. And then the other question is, would that precipitation really fall into Wyoming, or would it actually continue and maybe move to Maryland, or somewhere farther east? Okay, so we don't really know, because microphysics is pretty complicated. So we haven't done that study, but we could do this in this model study, because we can, again, compare the reference with the non-reference. Again, the other thing that we also have to consider now, all the Western states are cloud seeding. And usually, again, Idaho Power, they're also measuring the silver content in the water and in the snow. And again, they don't see really elevated levels that are beyond to the background silver levels. But again, if we are now starting to seed every mountain range over the entire winter, that might actually be a different topic as well. Again, there's very little research in that. I don't think any research in that. I know that some of these agencies, they do test the water, but there's really no comprehensive research behind that. So these are usually the conspiracy, the easy to address conspiracy theories about cloud seeding. Another thing that I often say is, again, once you start seeding, the material is in the atmosphere for maybe 2, 3, 4 hours, and then everything falls out and everything's back to normal. So it's not reversible, but you can stop it easily at any time. And the other interesting thing is that every time we are getting into an airplane and we are flying through a supercooled liquid cloud, we are seeding the cloud. So everyone is seeding intentionally or non-intentionally. So these are usually the questions that I have to address around the conspiracy. And then there are, of course, the really wild conspiracy theories that this is another seminar topic.
Thank you. So the last question I have in my queue is Isaac Marati. So Isaac, please go ahead. Anybody else has some last minute questions? Now's the time to think about them.
Yep. Thank you, Katja. That was a very interesting talk. So I have a comment on the microphysics. So we have been actually looking at different microphysics for a year. For frozen hydrometeors, I can give you a couple of names. For liquid, it's very hard to find something that really matches the radar. I have looked at Thomson, Abel 2012, which is really Thomson, and a few others, and none of them is perfect. So if you find something really perfect, I'll let you know. Yeah, but my question, and maybe you answered it, and it's not really I'm not into conspiracy theory at all. So when you are seeding, and I don't know much about the atmospheric chemistry, so when you are seeding, and let's say it rains, are you really generating acid rain? If you, let's say, do it over farm, like the farmlands or over cities, are you really generating acid rains, or this is not something to be concerned about?
Yeah, good to see you, Isaac. Yeah, so you're basically having silver in your hydrometeor, and that's meteors, and that's the silver that will end up in the snow and will up in rivers and will end in reservoirs. So again, there's really not a lot of research on like the impacts. One thing that I learned as well was that we actually have a certain silver level, like a background level in our river streams, especially in the West. And so again, there are no requirements that these companies have to provide numbers or do regular measurements. Idaho Power Company, they do measurements of like how much silver ends up in these streams. And again, based on what they measure is basically a similar magnitude, order of magnitude than what the background silver concentration is. But again, being said, again, if everyone seeds now and everything merges into the Colorado River, that might be a different topic. But again, there's very little research around it. Yeah, and also even the impact on silver on the human body. I mean, I try to Google some of that. I mean, there's some studies that say your skin color changes or makes it a little bit more brown. But again, there's really no deep research into that as well. So that's what I'm saying. It's like the industry is really so far ahead of the science, and there's so many research questions that are really interesting that could be addressed around cloud seeding. Again, generating trouts, and it's like, okay, what are the downstream conditions, and what is the impact of silver? Again, this goes back to the efficiency, that how much silver iodide are we putting in? And we are seeing the regeneration on the top of the cloud, which tells us we have a lot of INP, or we have a lot of silver iodide still lingering in the air, generating more precipitation. And the numerical simulations actually show that we have a lot of silver that is not activated, which means we are basically overseeding the cloud. So is there some research we can do? It's like, what is really the optimal amount of silver iodide that we need to put in these clouds just to extract all the silver, the supercooled liquid water?
So you don't need any special permits to conduct this, right?
No.
Okay.
I mean, interesting enough now is that a lot of states now introducing legislation, and this goes back to the contrail conspiracies, that they do not allow any kind of, not seeding, but even putting anything in the atmosphere. And it's really funny because Jeff French just testified in Wyoming, because it's written in a sense that anything is covered. You basically could not do any commercial aircraft. I don't know about cars. So anything that's voluntarily put in the atmosphere. Again, it's targeted to address the contrail issue, but cloud seeding, of course, falls under this as well. So we don't know where this goes. So it was declined in Wyoming, so it didn't go through because, again, it was just far too complicated, because what do you do with commercial aircraft or air traffic? But again, these might be things that actually come our way, but rather than that, there's no regulations around it.
Thank you.
Thank you. Do we have any other questions before we close our seminar for the day? Okay, well, thank you so much to Katja for giving us this great talk, and thank you so much for everybody for coming and giving us a lively Q&A session. This seminar will be on our ESSEC YouTube channel by the end of the week, and our seminar series will continue. Just a reminder, Monday is a federal holiday, so our seminar will be on Tuesday, same time, 2 o'clock. Thank you, everybody.
Thank you so much. Take care, everyone.
Take care.